You guys ready for the end of the semester? So I made a mistake. I went into our office yesterday and decided, oh, I'll just go teach from Sac State Monday night. It was a mistake because they have the heating and air conditioning turned off in Riverside, and it was so hot.
Wait, how come you're like teaching one class in person?
No, not in person. I just thought I would go and drop in because I haven't been there all semester just to see what it was like. And so I sat in the faculty workroom for my class, and it was like I was baking. It was so hot.
Yeah, I could imagine they wouldn't turn on a whole building AC for like a few people.
Mhm. Okay, so I'm looking to see where we left off. Um, so we talked about the whole element formulation last time and what that means. So remember, the element formulation consists of three things: the shape functions, the mapping of the parent to the physical element, and that's usually an isoparametric type mapping, and an integration rule on the parent element. So all three of those things make up a parent in element formulation. And in general, when you're comparing different finite element software codes, and you were to take a simple beam calculation and you calculate one of them in each one of those software packages and you get slightly different results, that's likely why, is they have a little bit different um, element formulations. Even if you pick they're the same number of nodes and things like that, there's going to be nuances in them that are slightly different. There's going to be slight variations in what you get there. So I think what I'm going to do today is go a little bit further on this element into these details. Um, and then I have one last kind of problem start to finish that I think I want to do, but that's going to be on Thursday. I'll do a problem kind of start to finish applied to like a beam. So we'll take a beam, and I mean, it's still conceptual, um, but we'll have a beam and we'll look at axial extension, vertical displacement, and plane angle. So if it had a cross section, the angular rotation. So all three of those parameters will basically make up our equilibrium equations and our boundary conditions. So we'll go through or write the weak form, strong form, write out the notation for what the Guillercian approximation would be of the weak form. And that'll turn into our integral that we solve with our stiffness matrix. It's like element formulations. Yeah, and we'll end up with a K matrix. So basically the K matrix that we have to apply the integration rule. So we won't get into the details of the integration rule on that problem, but it'll take you from a beam problem that you know all the way through this FE process, and you'll be left with three stiffness equations that you would solve by the numerical using numerical integration rule. Trying to decide if this next stuff I was going to give you is going to be useful or not. Out of order. Sorry, my notes are out of order here. Yeah, okay. It's going to be a lot of writing, unfortunately. So, we need our whiteboard up. Hey, blue. What color? Did we get rainbow last time?
Yeah, rainbow.
Nice. Okay. That's kind of cool. Today's the 11th. Today's May 11th, and my notes were taken when I wrote these notes. I wrote them on May 1st. Just a different year. Kind of cool. So, stiffness matrix. So remember, we have this K underscore alpha beta M. So we're talking about a stiffness at an element. And this was equal to the integral over this domain omega of B alpha M transpose C B beta to the M J C D nu. And we want to choose the integration rule. On our domain, omega, on omega, so that the approximate to K alpha is good, and this is very subjective. So we want to try to integrate this as best as we can. That's essentially what this is saying. It's kind of like of course you want to do that. That should be our goal. But it's kind of setting yourself up for expectations that you're not going to integrate it perfectly. It's going to be an approximation with error associated with it. So you're not getting an exact solution. It is possible if the integration rule is of sufficiently low order, integration rule is of sufficiently low order that k to the m is rank deficient. At least by more than it should be. And essentially what this means is you need to look for equilibrium and no rigid body motion. In 2 dimensions, your element stiffness matrices should have rank 2 by n. So it just depends on your number of nodes. And in 3 dimensions, it should be, rank should be 3 by n. So you're looking for the shape of the matrix. So a rank deficient stiffness matrix can lead to this phenomena called hourglassing. Where the stiffness required is in the null space. And thus has no stiffness. So this K matrix, this we're calling this is, K to the M. It's a matrix. So let's say that we have a 2-dimensional matrix. And we have a K11, K12, K21, K22. Okay. So we've got this K matrix. So this is just K alpha beta M is equal to this guy. So we have the stiffness matrix. We have a 2x2. Great. What would happen? So what is 1, 1? What is this referring to? So we're talking that we have a two-dimensional space. It's 1, 1 is tension in the one direction, right? 2, 2 is pure tension in the two directions. So we have a two-dimensional element. K1, 1 is this way, right? K1, 1's this way, and K2, 2 is this way. What happens if we actually have a loading where K1, 1 needs to be present, but in our matrix, it is actually a 0. We have 0 stiffness, right? The thing's going to collapse in itself. It's a little more complicated than this, but that is what you're looking for, and that's what it's kind of referring to in null space. But what can happen, this hourglassing effect, is if you have an element, and this is usually happens when you have insufficient, talking about the rank, it's insufficient number of integration points, insufficient nodes, is, let's say we pick an element and we have a single integration point in the center. A single integration point with a square element like this could lead to a deformed shape of this element that is kind of like this. So what happens in these particular situations is you have a loss of volume. What we shouldn't have happen with these elements is they should change shape, but they shouldn't lose any volume. So if you have something in your stiffness matrix that has gone wrong, you have a 0 where you shouldn't, or you have an improper number of integration points with your element, you can get a negative volume, and it's called this hourglassing effect. And what it comes down to is, if you have a single integration point here, and we find our stiffness characteristics of this, there's not sufficient stiffness, a mathematical stiffness representation for this square to keep this from happening. So it's just something you have to watch out for when you're doing. I mean, your software codes should capture this type of stuff for you, but it is something that you could get more than likely errors when you're doing your solutions and things like that. So it's an indication that you have a rank deficient stiffness matrix. A solution could be changing your integration rule or upping your integration rule to a higher order. Excuse me, so you have more integration points. So in this particular case, it would be solved by, maybe you change it to a 4-point integration rule rather than a single point integration rule. Okay. Now, suppose we don't want green. Suppose we use isoparametric. Suppose we use isoparametric element. Suppose we use an isoparametric element. And the shape functions, I'm just going to say ASF, shape functions, are polynomial in C, nu, and what is that guy called? Xi. So for three, that's our 3 dimensions. And the question is it even possible to exactly integrate K alpha beta to the M using Gaussian rules? So recall that Gaussian 1D with the number of sampling points or the number of sampling polynomials or number of sampling points of order 2 times the number of sampling polynomials minus 1. I don't know if we wrote it out exactly that, but kind of indicated that. And the Gaussian only integrates polynomials. So our Jacobian is x1 c, x1 nu, x2 c, x. These are polynomial in C and nu. But our B matrices these are shape functions in alpha comma 1 and alpha comma 2. Bring back shape functions. This we're equal to the inverse transpose of N1C, N2 nu. These are not polynomials. Remember, our K matrix has these B terms in it, right? It's the first one is B alpha, and the second one is B beta. So our Jacobian has polynomials, but our shape functions do not. So conclusion, for distorted elements, is our B matrix alpha, M transpose, stiffness matrix C, B matrix beta, M Jacobian. This argument right here is not polynomial. And the Gaussian only integrates polynomials. So therefore, no Gaussian rule is sufficient to exactly integrate. You're like, great, you just wasted a whole semester of my time. It is generally believed that full integration supplies a sufficiently accurate stiffness matrix for all purposes where full integration means that our stiffness matrix on our element integrated over our domain omega E beta n j dc union is exactly integrated. For undistorted elements. Um, elements for which our Jacobian is constant. So this is just a fancy way of saying is, yes, we don't have a polynomial. Yes, we understand a Gaussian rule isn't sufficient to exactly integrate it, but because people have been using this for so long and studying it for so long, and they've done this enough. It's a common kind of professional courtesy, I guess, that it's considered that it's sufficiently that accurate K stiffness matrix, K matrix, can be what they consider a full integration. You're going to integrate over the entire domain, and it provides a reasonable or a sufficiently accurate K matrix out of it. So it's basically just assumed to be the same as exactly integrated for the undistorted element, with the caveat that your Jacobian is constant. So it's kind of like an academic courtesy, like I said. Now, for a 4-node quad, or 4-node quad, the integrand is at most quadratic. So highest order terms being psi squared, or psi mu. Therefore, full integration is achieved, full integration with a 2x2 Gaussian rule. An 8-node the integrand has psi nu, mu psi, psi, yeah, I said that was psi earlier. It's not. I think sometimes it's referred to as zeta. Doesn't really matter. It's the third axis. In our C space. And this is multiplied times yeah, and so this has full integration at a 2x2x2 full integration 2x2 Gaussian. A 9-node Lagrange in 2D. For this one, every shape function in alpha has psi squared, mu squared, and psi nu squared, comma, psi squared mu times psi mu squared mu, which leads to full integration at a 3/3 Gaussian. Now, all this is really saying is, it goes back to the whole thing. Don't believe what you're doing is an exact solution. We have a boundary value problem. We're going to try to solve it. We have these shape functions that have these approximations in it. We have these weight functions that are in here to help us solve this as part of our minimum potential energy theorem. And then we have this integration rule. And it's basically, don't kid yourself. You're not getting an exact solution. Is that kind of clear to everybody that that's, I mean, maybe the mathematics doesn't make sense, but at least conceptually you understand that that's what's going on here, is we're just talking about this as a numerical approximation to that boundary value problem. We're not getting an exact number. And this is all saying, yeah, amongst friends, we all just agree that we're going to call this a full integration. And we're going to say that it's essentially close enough to exact. So, you know, if you want to pick a fight with your colleague at work and you guys are doing FEA stuff, you can, you know, start picking on them and say, oh, this is an exact solution. No, it's not an exact solution. It's a full integration and so on. It's an approximation. Kind of like reading a tape measure or something like that. So is that sinking in?
Yeah.
Yeah. Okay. So don't believe, you can't, that's like the worst thing you can do. And I don't know if any of you will ever come across people like that in your careers. I have. I've come across one of those people that I don't think had this theory and started doing a lot of FEA work in practice and got to a point where they just started believing the results were like perfect. Like they were absolute, they're exact, you know, they are the answer. And I think when you get to that state of mind, you've kind of lost sense of what we're doing. That the finite element, the idea of finite element analysis is really just, it's just a tool. It's just a way to solve a boundary value problem, and it's going to give you a rough approximation. And that rough approximation is pretty darn good. You know, if you were to go test it and put strain gauges and things like that on things, it's going to be very, very good. But, you know, if you get into a water cooler conversation with a mathematician, they're going to eat your lunch because it's not an exact solution.
Well,
really,
even if it was, even if the integration was exact, you still have so many other assumptions going into your finite element model that you still don't have an exact solution because there's assumptions layered on assumptions.
Assumptions layered on assumptions layered on assumptions. And I've never seen anyone like really try to lay out like what the error could be for a really simply supported beam type problem. I actually think it would be a really neat master's thesis for someone, to do that, like maybe take, if any of you are looking shopping for master's theses ideas, you could take like Saint Venant's principles, and Saint Venant's has a couple of different principles where you look at basically axial shear and bending. You could look at the like 3 scenarios with a very simplified geometry where you could write out what that boundary value problem is and solve it by hand and get an exact integration, right? Where you took into account the shear warping and everything, and you found the exact solution. And then you go through and you do this from a finite element perspective and try to quantify the effects of some of the different assumptions in the mathematical routine, to show where the actual the error, identify, is it on the conservative side, meaning does it lend a larger displacement, or is it non-conservative and give you a smaller displacement? And does everyone know what I mean when I say conservative with regards to the displacement? If you have a simply supported beam, beam, and let's say it's maybe a little bit more complicated than just simply supported, but let's do something like this where this is on rollers, frictionless or something, and we applied a load, point load to it, and we get some displacement out of this guy, right? So if we have a large displacement, would this be versus small? And the reason I'm talking about displacements, because that's ultimately what we're solving here, right? We're solving a stiffness. We're solving for K. And we're solving for, very rudimentarily, force is equal to Kx, right? It's this K is the stiffness matrix. This is the K alpha beta M. It's stiffness. It's much more complicated but that's really what we're solving here, is for that stiffness value. What is X? This is displacement, right? It's right here. So a large displacement will yield a large or a small strain. A large displacement is going to give you a large strain and a large stress, versus this is going to give you small, right? So if you do a calculation and your displacement is bigger than what you would from a closed form solution, this would be considered conservative because it's going to yield a higher stress, a higher strain. And these are the criterion that you would base your design decisions on, more than likely. It's, I don't want to exceed a certain percent of my yield stress, or I don't want to exceed, a certain amount of plastic strain, if you're going plastic or not. So if someone were to dissect this and really identify where the conservatism lies, I think it would be a really cool thesis. Okay. Let's see. I don't know if this is Yeah, I don't think this is useful. We don't need to approve. Yeah, okay. I think that's it, except for this last problem. I don't know if it makes sense to start it tonight. I think I just want to do this problem on Thursday, kind of start to finish. So it's kind of the FEM applied to beams. So where we'll end up with is we'll end up at a K matrix. So we won't go through and do the integration rule. But we will see stiffness matrix and global stiffness matrix, and then we'll break it down into an element stiffness matrix. 3 of them actually, 3 integrands, and then those 3 integrands would, in order to solve the problem completely, you would apply the appropriate Gaussian integration rule to get your final answer. 513. Yeah. And then yeah, I think that'll be it. Okay. Yeah, I say we cut it early for tonight, and then also on Thursday we'll go through this one last problem. Yeah, and that'll kind of close things out. So you'll see a beam problem associated with this that have 3 components that we're looking at independently. Okay.
Sounds good.
All right. Well, have a good night. We'll see you on Thursday.
Thanks.
Thank you.
Thank you.
Supervisor.